let's look at the fundamentals of probability and statistics that are used in AI. If you can understand what I cover in this video, you really shouldn't have any problem understanding anything in AI. It's all built on these basic steps. That may seem like an exaggeration, but the more you learn, the more you realize that all the complexities that get added to make all these different AI tools, sooner or later, are going to come down to these basics of probability. So, probabilistic methods. There are four, well, to back up, before I say that, let's just recap what we've already seen with probability. We've already seen a kind of probabilistic ranking, right? Probability is what is most likely to be this thing. We make some prediction based on a probability. So if you rank your spelling candidates only with their edit distance, and you put the 1 edit distance words first, and then the words that are 2 edit distance away, and then 3, and then 4, that is a kind of probabilistic ranking, because you are saying probably the word that is, or the words that are only 1 edit distance away are most likely what the person intended to spell. So that is a kind of probability. So if you see a word that's spelled C-O-U-R-C-E, and you calculate the edit distance from that word, which is not a word, to all the words in the dictionary, and then you choose the ones that are 1 edit distance away, you're saying the first word, or the first group of words, are more likely the intended spelling than the second, and the second word is more probable than the third, and so on and so forth. So if you used edit distance and then maybe some information about human behavior, such as spelling errors tend to occur in the first letter, the first 2 letters, and you add, you count that probability, which we'll look at in just a second, and you kind of multiply the 2 together, or you put it further up, maybe no math, you just say, hey, this is in the first letter, therefore it goes up. It's a simple if-then rule. That is still feeding into that probabilistic ranking, without necessarily using probability formula or math that goes with probability. So let's take a look at that kind of probabilistic method. So probabilistic methods, particularly those, really any, all probability, but those that are used in AI as well, no matter how complex it gets, can be summarized in 4 very basic steps. First of all, you take some data and you account the occurrences of the phenomenon you're interested in the context that you're interested in. And we'll look at examples in just a second. Then you calculate a fraction or ratio of the occurrences out of all the possible contexts, or all the possible occurrences, within that context, right? So the occurrences of the phenomenon you're particularly interested out of all the occurrences in that context that you were interested in, okay? Then you take that fraction or ratio and you turn it into a probability, likelihood, or weight. But basically, you talk about it as if it was a probability instead of just a fraction. So the difference, there is a technical difference between probability and likelihood. I think it gets covered in one of the videos. We don't care about that in this class, but I want you to put that up there so you know that these are going to be used interchangeably. Another one you might hear is weight. This happens when you put a bunch of probabilities together and multiply them to get a different, like a final probability. Again, as far as this class is concerned, you really can think of them interchangeably. Weight happens when it's part of a bigger probability calculation. But for all intents and purposes, the fraction is a probability. All right. So we talk about it as a probability, likelihood, weight. We turn it into it by just saying this is a probability. Before it was a count, now it's a probability. And then you use that probability, that fraction ratio, which you now think of as a probability, to predict future occurrences of the phenomenon you're studied in the same context in which you counted it. Those are the 4 basic steps of any probability, use of any probability or statistics. It can all be boiled down to that. Let's look at an example here. Now, our context to kind of recapped from last week was if you want to rank spelling words, and whether of all the words that are 1 edit distance away, which one is the most likely? Which one should you rank first? But let's look at a situation that's even more simple. Let's say we want to get started building a spell checker that can identify misspellings either where there is no dictionary or misspellings that create a word in the dictionary but still might be a misspelling. So in that case, one question we might want to ask that might be useful to model and tell our computer, this is information that will be helpful to you, is what's the probability of there being a misspelling at all? If you have, right? And okay, well let's go on. Let's just go with that. Simple. What's the likelihood? All right, we want to figure out. And we can think of different ways to use this. So the first thing is to look at, we want to know how many misspellings occur on average, or to get an idea of how likely it is. So let's say, okay, so let's not say, this is how we're going to go about it. You're going to get a bunch of text, or as many texts as you can find that represent the context you're interested in. So monolingual, maybe it kind of depends on your users. Maybe they're bilingual, maybe they type in both, maybe they're non-native speakers, maybe you need to just find the context where everybody who's typing is a non-native speaker. Okay, so here's where it starts getting complicated with probability. What you're going to count and like your phenomenon of interest and the context in which you want to count it is going to depend on what question you want to ask, or in the case of technology, what tool you want to build, or for whom you want to build the tool. So if we want to, let's say we want to build a spell checker that is customized and idealized for optimal for non-native English speakers to help them, then our context of interest would be people who are non-native speakers that are typing in English, right? So then we're going to count the misspellings in all the typed text we can get our hands on that were made by non-native English speakers typing in English, okay? So statistics is one of those things where it almost seems like you have to change the data to fit your question, which is a big no-no in science. And that maybe this is why there's a famous saying that goes something like, well, there's white lies, and then there's lies, and then there's statistics, right? Because they don't seem reliable and they seem kind of weird. So it's just a caveat. There's no answer ahead of time. You have to know what you're interested in, and you have to know what context is needed for your tool. And sometimes you're like, well, this is a context I want, but I just can't find enough texts that are typed by non-native English speakers. Maybe they're not labeled as such. Maybe there just aren't a lot of non-native English speakers typing, or they don't want to work with you. So sometimes you have to go with second best. So let's say we get a bunch of typed text in English. We get some volunteers, non-native speakers to type, perhaps. And okay, that's our context of interest. Now we're going to count the number of misspellings. All right, so that's step one. So it's actually big, right? You have to identify the context of interest. You have to find the data. But once you find it, then you just count all the misspellings in the monolingual type text by, say, non-native English speakers, okay? Once we have those counts, we have the counts of all the misspellings. We also have the counts of all the words in that text. So let's calculate a fraction. We're going to divide the number of misspelled words, so every occurrence of a misspelling of a word, by all the words, all the possible occurrences, all the situations where they could have had a misspelling, which is all the words. So we'll divide the number of words that are misspelled divided by all words in our typed text. And from that, we'll get a fraction, which can be presented as a ratio. So if there's 400 words and 100 of them are misspelled, then the ratio is 1 misspelling for every 4 words. That can be presented as a fraction. 1/4 of the words are misspelled, or as a decimal, 0.25 of the words, or as a percentage, 25% of the words are misspelled. Right, it's all equal. So take one of those. The fraction or the percentage, we have it. This is what we've counted. So now we're going to turn it into a probability, and we just change the way we talk about it. 1 in 4 words in typed text by non-native English speakers, if that's our context, is probably misspelled. But if you think about it, we just made a huge assumption. We made the assumption that how all the non-native English speakers that we gathered data from will in the future continue to do the same rate of misspellings, and that their rate of misspellings is going to be the same as all non-native English speakers. That's a huge assumption. But if you get the right context, if you get, enough context where you can, okay, well, what about, we'll average it between non-native, or native Spanish speakers typing in English and native French speakers and native Swahili speakers or something like that. So you can get enough context. It turns out, at least with language, it works. It kind of makes sense. Humans are humans. We're all kind of, we're all unique, but we also live in a human body. We have similar, if not the same, limitations of mind and physical energy and attention span. So there's a lot of patterns that repeat. So it turns out it works, but it is a huge assumption, right? So something to keep in mind. That's what happened. It seems like a very simple step. We made a huge assumption. One thing here to keep in mind then is because it works because human behavior with language is, just human behavior has some patterns in it. This is similar to getting a bunch of data, let's say a coin. You aren't allowed to weigh the coin. All you can do is see the results of the flip. And you have to figure out whether it's an equal weighted coin, so equally likely to land on tails or heads. If you do one flip, right, you can ask as many flips as you want. If you ask for one, it lands up tails. It would be pretty foolish to say, well, it's 100% probable to always land on tails, right? That's not enough information. So do it another time. It might still be tails, it might be heads, but even at that point, even if it's heads, tails, it's still not good enough, not smart to say, oh yeah, it's 50-50. But as it turns out, the way that things work is the more flips that you do, say 50, 100, 500, the more you do, the closer, if you keep on counting and dividing, so counting the number of times you get tails divided by the total number of flips, or the number of times you get heads divided by the total number of flips, the more instances you look at, the more occurrences you look at and add to your count, the closer your fraction or your ratio is going to get to the actual reality of the coin. So after 100 or 500 flips, you're going to find that it's pretty close, if it is a 50-50 weight, to 50-50, to 50%. And at that point, you can say, okay, I'm going to make a prediction. So that's the fourth step. I'm now going to say, I have enough data, I've done enough counting, I've made the assumption that the behavior in the past will continue in the future, and this go from it's probably misspelled to now I'm going to say in this new text on which I have done no counting, I will say 25% of those words are misspelled. That's a prediction. And that's it. That's how probability works, and essentially that's how LAI, language technology, all modern AI works. It works on these four basic steps. You get a lot of data, you figure out what phenomenon or phenomena that you're interested in which context that you want to build or for what audience you want to build. So you figure out the exact context you need. You count the occurrence of the thing you're interested in divided by the context, the occurrences within the whole context. So number of misspellings, number of times that this particular audio clip got transcribed as a T, whatever it is. You do the fraction, you turn that into a probability, whatever the number is, and then you get new data that you don't have any counts for, and you make a prediction based on what you've seen in the past with all the counting you've done is going to be true in the future. If you can understand that, then you have a grasp on all basic AI. And you may have never done the counting yourself, but I'm sure you can understand this because you've used the same basic principle in your life. Almost guarantee you have. For example, if your sister has been late for the last 10 times you invited her to go somewhere, or 8 out of 10 times, you may or may not do the counting, but you probably picked up the pattern. You're going to say, probably the next time I invite her, she's going to be late again. So you say, right, calculation. There's a probability there. May not have done the exact number, but I know it's greater than 50. It might be close to 100%, so I make a prediction. She's going to be late next time. And then you build a useful tool out of it, which is, in that case, go and tell mom, hey, mom, when we all go out together, tell everybody else to be there at 4:15, tell sister to be there at 4, and then we can all leave on time.